It was indeed at Hooft, I think, who was, as I said, thinking about black holes, even ignoring what happened in string theory. But he already had the idea that black holes are special in the following way, that they're not only the densest objects, they're also the objects that contain the most information that you can put inside a certain volume. So he said basically the following: take a certain part of space inside a sphere, and I want to put information inside. I can do this by adding particles and giving them properties like, well, they have spin and they have charge and all kinds of things that I can count. And I can bring more particles in, and eventually I'm increasing the information. But eventually, when you bring in so many particles, you also, of course, the gravity comes in, you can create a black hole. And his argument was that the most information you can put inside a volume is given by if you would make something like a black hole. And then we know how much information a black hole has, namely it's given by the area of its horizon. And the conclusion is kind of strange, namely that if you have a volume, which we normally think about as growing with the radius, well, in a certain, well, it's cubed because it's like height times this, whatever it is.
Width and depth.
That's how a volume grows. It's like the cube of the radius, while the area grows like the square of the radius. And so the funny thing is that inside a volume, I cannot put arbitrary amount of information, not in every point. I mean, it has to be equal to the area measured in a certain unit that we call the Planck scale. It's a large number in general because the Planck scale is a very tiny scale. It's like 10 to the minus 33 centimeters. It's really a small number. That if you would count that for a sphere of this size, it would be, well, enormous. I don't even know how to express this. I mean, I think the outcome of his argument was basically that if you have indeed information inside a volume that goes like the area, it also means that you basically can describe everything inside of a volume by going to the boundary and putting there all this information. So the larger the volume, eventually you will get some big sphere, but then all of that's going on inside this volume should be described by information that's sort of projected onto the boundary of that sphere. And this is what he called a hologram. It was later indeed seen also by Susskind, and who realized this well, the power of this idea, and that's what eventually became the holographic principle. It was proposed sort of in the middle of the 90s. And one of the beautiful things that happened quite soon after that is the breakthroughs that we had in string theory. I mean, around that time, we started indeed understanding more about what the information is associated with black holes. And so this holographic idea then got indeed realized also in a setting that we could derive from string theory. So this is what made us all convinced that indeed this holographic principle kind of holds, and that it's really something that's very deeply connected to how gravity and quantum mechanics work together. There's something else I wanted to say. Yeah, indeed, the holographic principle now, actually, what I wanted to say actually is that it, of course, goes back to what Bekenstein and Hawking did, namely, they had their formula for the entropy of a black hole, which was the area of the horizon. And now it became a principle that was much more general. I mean, it's not just about black holes. It basically says that any part of space-time, the information that I can put there must be sort of bounded by the area that is bounding that region. And this idea has really shaped the way we think about gravity and quantum mechanics now for already a number of decades, and it's leading us to sort of, well, deep insights about how gravity and quantum mechanics work.
Okay, I'd like to get back in a minute to where string theory connects with the holographic principle to help make sense of Bekenstein-Hawking radiation. But first, if it's okay, I'd like to explore the holographic principle a little bit more. And just to make sure that I have it correctly, we can just in a definition, the holographic principle is that you can describe everything in a given volume with information on the boundary of a surrounding two-dimensional surface. Is that a good encapsulation of just what it is in a slogan?
In the slogan, I think that's correct. I mean, I don't think we have a full understanding yet of what it means. We have some particular examples that we found in string theory, where we even have a more precise description or definition. But you're right. I mean, so the way we think about the holographic principle is that to describe everything inside a certain volume, we can describe it information that's sort of written or living on that boundary of that volume. And just like a hologram, you're basically reconstructing a larger part of the three-dimensional space from something that's, say, two-dimensional.
Okay. And then the question that comes to mind is more philosophical, I think, here than physical, maybe. But I understand that the holographic principle extends beyond just black holes to the universe. So we could, in principle, describe everything in the volume of the universe with information that is encoded on some surrounding two-dimensional area. And the question that I have, if that is right, is it's one thing to say that we can describe everything in this way. It's quite another thing to say that is the correct description of the universe. And what we experience is, in fact, a hologram, that the universe, the volume of the universe is this projection from a two-dimensional and surrounding area boundary. Do you think, or is it argued that is what the universe is, or just that's a possible description?
I like the way you phrased it, because I think there would be probably many colleagues of mine that would be agreeing with the strong version that you just said, that this is the way it is. Well, I don't think it's also the way. I mean, I think in practice, it's not how we should think about it. It's more like a bound on the information. And it may also not be the most, indeed, and this is sort of what we have been working on in the last decades. Having everything on the boundary is not the most practical way of describing what is going on here in our universe. Here we are talking, and we are living our lives. And it's very weird to think about that really is just some projection, some whatever reconstruction of something that's going on the boundary. But the principle, I think, helped us understand better about what quantum gravity is, and also indeed how much information we need to describe everything that's happening, say within the universe even. But I don't think it's the final way we're going to be thinking about it. I mean, also the way we want to describe the physics and everything that's going on in our experiments or our observations, having this picture where everything should be described on the boundary is not the most practical way, or even the most maybe fundamental way of thinking about it. It's more like, I think, as I said, an upper limit of how much information we need, but also maybe something that I think eventually become more a feature of the microscopic description than really the way we should think about it as a principle.
Okay, so for you, maybe the weak version of the holographic principle is that it's a useful tool for achieving a better understanding of whatever the universe is, rather than an insight into, let's say, the fundamental metaphysics of the universe.
Yes, and I think raising it to a principle that should be really imposed on our microscopic theory, I think is going too far. And I'm certainly one of the people that are arguing a little bit against this, but I'm only one of a few people. I have to say many of my colleagues will probably go as far as basically saying that holography is the most fundamental discovery, and we should that's how we should think about our universe. I don't think that is practical, and even also fundamentally what is going on.
I'm talking to your colleague Juan Maldacena in a week or two. I imagine that he's one of the people who has a stronger sense of holography. So I'm looking forward to asking him about that and some other string theorists. But before I have that conversation, this is the last question I have about this dimension of holography. But for those who do think that everything you and I are experiencing right now is a projection from this two-dimensional boundary, what sort of makes this volume a project? Like, what is doing the projection? Or because the holograms that we're familiar with are kind of like illusions. They're just sort of plays of light, maybe, but there's substance to this projection. Like, what is bringing this to the interior of the sphere from the outside?
Well, it is also the gravitational field. I mean, if you have a mass, you can measure its gravitation by going further out. You can feel the force. And so the same you can do with charges. You can feel the electric field. And so one of the things we have learned is that we can even measure the mass or the charge by going to infinity and basically measure what's the electric field or what is the gravitational field there. And so everything in our universe also, how should I say this? I mean, there's some way in which when something happens locally here, it's going to give a signal that goes to the boundary. And so somehow the information of what I do in the space eventually will be reaching the boundary. And this reconstruction of what is happening inside the volume somehow uses sort of the inverse. I mean, you basically have to understand how signals from the point in space goes to the boundary, and then you sort of reconstruct that from the boundary. So there's some way that the inside of a volume communicates with the boundary, so that the information is basically projected on the boundary, and we have to sort of go back and see what we can read off from the boundary, what is really going on in the inside. So this is kind of the language that people have tried to develop in how the inside, we call this volume, by the way, the inside, we call this the bulk. It's sort of where we are inside, and we have the boundary. And so there is a dictionary that translates things that happen in the bulk, namely in the volume, to things that happen on the boundary. And that dictionary is kind of what we have been thinking about. And it's possible to make that translation, in particular toy models, I should say, which don't look like our universe. They are universes that, have no dark energy, for instance, in them. They are universes that, unlike our universe, have sort of a negative curvature. I mean, it's not curved in a positive way, but in a negative way. So those are special spaces where we can do this mapping from the inside, the volume, to the boundary, and we kind of understand it there mathematically, but we don't have a full translation yet. But there is ways of understanding it there.